Hello, my name is Björn Askeland. This is my fourth video about Riemann's hypothesis. Today I'm going to show you how to calculate Riemann zeros with the Euler product and with the condition Riemann left in his trash can. I did my first version of my Riemann proof already in 2008, but I did not understand the connection between the Euler product and the condition which occurs in my proof until January 2023. I gave up publication of my proof in 2018 and submitted the proof to YouTube. The weakness of my proof was that I could not calculate any zeros. But since January 2023 I can calculate hundreds of zeros. I will explain these calculations to you in this video. What you see is how Askeland's condition is used to calculate the phase diagram of Riemann's analytic continuation discretely using the Euler product. The discreteness is caused by solving Askeland's condition, which is the equation you can see above the plots. The blue curve is the phase diagram of Riemann's analytic continuation. The horizontal axis is the imaginary axis. As you see, the blue curve has 10 phase jumps of pi up to imaginary value 50. These are Riemann zeros. As you see, the red discrete plot follows the blue plot. You can also observe that the maximum prime Pmax is increasing and that the red line segments and dots move to the left. Pmax is the maximum prime used in the Euler product, but Pmax is also the length of the zeta function as a sum. These calculations are the final confirmation that my Riemann hypothesis proof is correct. My theory is now completely independent of Riemann's theory. I also claim that it's very unlikely that Riemann's hypothesis can be proven with his own theory. I will in this video try to explain that Askeland's condition will cause a paradigm shift in prime number theory. This plot is historic because I discovered in January 2023 that the frequency of oscillation of the EulerPhase is the same frequency of oscillation which appears in my Riemann hypothesis proof. This oscillation occurs with the same frequency inside the zeta sum formula you see below the plot. The red plot is now the total phase of the Euler product. Observe that the wavy curve of the phase of the Euler product has higher amplitude for lower values of the imaginary number on the horizontal axis. The Euler phase seems to swing with a certain period. This is the formula for the Euler product. You get the phase of the Euler product by adding the phases of each factor of the Euler product. You just saw the phase of the Euler product being used outside its domain, which is inside Riemann's critical strip. The red plot is the phase of the Euler product when the maximum prime of the Euler product is 9973. Let us see how the Euler phase changes when we include more primes by increasing n. You can now see that the amplitude increases and that the frequency of the oscillation increases slowly with an increase of the highest prime of the Euler product. I'm running this until n equals around 10 millions. The amplitude just gets bigger and bigger and the frequency of the oscillation increases slowly. Askeland's condition calculates the locations of all these zero crossings of Riemann's blue analytic continuation. Let's go to my proof and look at the condition which gives the oscillation. Equation 11 is an expression for the zeta function as a sum from my proof in video 1. It has a condition. I show in my proof that the condition is infinite outside the critical line. The oscillating condition can only be zero on Riemann's critical line where the real part of S is 1/2. The condition is reworked in my proof to equation 35 on the critical line. The equation in the middle is Riemann's functional equation. It does not have a condition. Riemann threw it unfortunately in the trash can with his method. But it is the condition which explains where the zeros can be. So mathematicians are searching elsewhere for a solution. None of them are searching for it where the solution really is, in Riemann's trash can. That's why the problem is 165 years old and will get even older. Riemann's functional equation tells you that if you find one zero outside the critical line at the real part of S equals to 1/2, you have also found 3 other zeros. Complex conjugate symmetry gives you the second zero. There is also symmetry through real time of s equals 1/2 plus j times 0. And finally, theorem number 4. So Riemann's big problem is to show that these zeros can only lie on the critical line. But the solution is in the trash can. Riemann's functional equation can only conditionally have zeros on the critical line. That's why I claim that Riemann's analytic theory never can explain his hypothesis that all zeros are on the critical line. Let's study the condition in the trash can, which can be expressed as equation 35 on my proof. The condition consists of two complex numbers. I call them vectors for practical purpose, since there is a rotation. You can say that the vector rotates, but you cannot say that the complex number rotates. The vectors can only cancel by subtraction when the length of the vectors are the same. That can only happen on the critical line, where the real part of S is 1/2. As the imaginary part B increases, the two vectors start moving in clockwise and counterclockwise direction. When they reach 180 degrees, they cancel. This is the same as pi radians. So what we have to do is to calculate the phase of Osceolan's condition. The denominator does not oscillate. It will end up with an angle close to 90 degrees before you get to the first Riemann zero. So the oscillation is determined by the numerator. So what we have to calculate is the phase of n to the jb, which is equal to e to the j times the natural logarithm of n multiplied by the imaginary number b. The oscillating part of the phase is now the natural logarithm of n times b. And I get half a period at 180 degrees, or pi radians. Delta b for half a period is then given by pi divided by the natural logarithm of n. 1 period is then given by 2 pi divided by the natural logarithm of n. The frequency of this oscillation increases with the length n of the zeta sum. I have in video 1 proven that this oscillation occurs inside the zeta sum formula. Let's go back to the EulerPhase diagram. As you see, there are some oscillations between Riemann 0,1 at 14 and 0,2 at 21. In this figure, n equals 9,973. According to my proof, delta b for one oscillation should then be 2 pi divided by the natural logarithm of 9,973 is 0.68. The distance between 0,1 and 0,2 is 6.89. That should give 10 periods between 0,1 and 0,2. If you count the cycles, you will see that there are 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and finally 10. Now you should be able to have a theoretical understanding of what's going on in this video. I used the oscillating condition of my proof to calculate the zero crossings in the phase diagram of the Euler product. Then I see Riemann's blue curve as a discrete plot with its pi radian phase shifts. As you see, I am able to hit the blue curve independent on the length n of the zeta sum. That means that the zeta sum has a fantastic refactorization property. Now you just need to understand one more detail. It's not enough to calculate the exact oscillation frequency. It's also necessary to calculate exactly where the zero is. And you need to solve this equation, including the denominator, which easily can be changed into this equation. I have used the solution of this equation in all animations of this video. Conclusions. I have proven that Riemann's functional equation only can give zeros on Riemann's critical line. I have in this video shown that these zeros can be calculated with Osceolan's condition applied to the phase diagram of the Euler product. This means that the zeta sum can be factorized with Riemann's zeros. This means that the zeros must be included in the domain of the zeta function as a sum. If a recursive formula for prime numbers does exist, I think these three formulas are very important. This is the necessary paradigm shift I mentioned in the beginning of this video. It is a completely new path with Ascalon's condition as a key to the new room. I'm ending the video as I started it. I think it's wonderful that I'm now able to calculate hundreds of zeros with Ascalon's condition and the Euler product. I also hope that this will be discovered by those who think that Riemann's hypothesis is an important problem. Thank you for watching.